Alright, hi guys, welcome back to our discussion on heat transfer. So in the last video we were talking about some of the finishing touches with respect to the hot radiation room. Now there are three more tutorials of that are available. One is called the simple car solar panel, and that actually shows us how to use snappy hex mesh with buoyantSimpleFoam. So this is what we do. I have already run it. So we can take a look at the steps inside the all run file. Okay, so it does run a block mesh first, and then it restores the zero directory because there's a zero directory original, and then it does a surface feature extract. Now, whenever you have snappy hex mesh, it's always good to have this restore zero directory so that you don't overwrite the stuff in your zero directory file. Okay, so there's a snappy hex mesh overwrite, so it does use snappy hex mesh. And then it runs the buoyantSimpleFoam. So these parts are the mesh generation. This part is just running the case. So where is the constant? Where is the mesh from? We can take a look. It will be in the tri-surface, and then you have a simple car.stl. And the emesh actually I think came later on. And yeah, you may notice why all these things in green. Probably because the permissions changed. Not that they are scripts or anything, but if you take a look at the radiation properties, it's a different kind of radiation model. Of course, you still have a radiation on. Here it says it's a solar load. So basically, what it means is that it's only receiving radiation from the sun, right? And if you take a look to see whether there's the same G file in the original, we see that there is no G at all. Alright, there's no G file for radiation, but okay, we have a boundary field over here. So it means for the solar panel, for the reference wall and the Z minimum, this is a adiabatic condition, and for the Y min max whatever, this is an inlet outlet kind of thing. So what is the inlet outlet? I believe there's a zero gradient. I have to double check, but I think hold on. Yes, so this is a mixed condition. It applies to all variables. Okay, so it sets the patch to a user specified value for reverse flow, and outlet flow is treated as a zero gradient condition. So what it means is that, okay, let's take a look at this. So the inlet outlet is when it's going to a reverse flow, it's at a fixed value. So what's that fixed value? 300, because it says internal field. It's defined here, so it says 300. So 300 Kelvin will be the reverse temperature, so to speak. That means temperature coming in. If there's temperature coming in from the outside, it's a 300. But if there's more temperature, I mean it's a higher temperature that's coming out, okay, outflow is treated using a zero gradient condition. So zero gradients means you have this, meaning to say it's adiabatic. So I'm just guessing that when it talks about receiving radiation from the surroundings, you'll be basically at a 300 Kelvin kind of thing. But when it goes out, when it's trying to radiate out or conduct heat out of this box, and then it will be a adiabatic condition, which is pretty okay because air is pretty insulating. Excuse me. So this is the U boundary condition. Okay, so this is what it's like, and we can take a look in ParaView. Okay, so at least from this tutorial we can see that you can use snappy hex mesh with buoyantSimpleFoam. It's not too big of a deal, and we have demonstrated how to do snappy hex mesh properly in the intermediate tutorials. So yeah, we can try something perhaps in future videos when we look at more complicated solvers, because buoyantSimpleFoam is really simple. a case. It's a steady state kind of a calculator. And of course, whatever evolution of the, for example, hot room you're seeing here, this is just based on the iterations that the solver is running. It doesn't mean that this is the state is changing. The steady state is changing. Okay, because steady state is supposed to be constant through with time. So what you're seeing in this time here is just means it's the iteration. It just means that okay, the calculator is having more steps to solve a new temperature field, and this is what you get. So let's take a look at the car, solar car. Okay, simple car solar panel, and let's see what is there. Now, of course, there'll be a new radiation model. So let's use a wireframe. You can be able to see the car. Okay, you should be able to see the car here. Let's see. Now this will be good. Let's give it a T. Okay, and we'll rescale. Okay, so that's what the mesh will look like. Okay, so there's a car, and then there's this little block here that looks like a solar panel. So let's take a look at the 50, and we'll rescale. All right. Look at the 5, yeah. So the external side is pretty hot, I suppose, but it's receiving solar radiation. So you can see the you can see the flow of heat, so to speak. But you can see the temperature difference is pretty minuscule as well. You can see it's all almost 300. Okay, so it remains at 300 Kelvin. All right, but important thing to take note of this is that, all right, this is just another model for radiation. You can check out how to put this model in based on this file, right? You can edit it. I'm not gonna go through in detail, but this is where you can look. You can take a look at this as well, the boundary radiation properties, and then it will describe the radiation properties for each boundary condition. So okay, let's take a look at system, and let's take, VI constant, boundary radiation properties. So you see, solar panel is one, there's one for reference wall, one for Z-min, one for body bottom. Every of these boundaries will have some sort of absorptivity and emissivity. So I'm not going to go through that because it's getting a bit complicated. Okay, so before we go on to transient properties, transient solvers, we kind of want to look at the last model of radiation. This is called the finite volume discrete ordinates method. Let's see whether this is finished. Log buoyantSimpleFoam, because I'm running in the background. So let's go all the way to the end, and it's still running in the background, which is hardly a surprise. But let's touch fvdom hotroom.foam. Okay, so we can open that up as well to see what it looks like tentatively. Apply. Now rescale. Okay, so we need to look for temperature. So the finite volume discrete ordinates method, this will kind of make the radiation calculation more complex but more accurate. So we can take a look at the wireframe, scale temperature, then we can go up. Okay, scale again. Let me look for a nice one. Yeah. Okay, so yeah, apparently heat is not getting out very much from this hot box, so to speak. Okay, so maybe I'll change the scale from this to about 350. Then we can see that, okay, there's some heating at the bottom. So maybe I'll go to 330. And then let's go. See whether there's some, yeah, can see? There is some heating effect that's going on. So it doesn't happen as fast as the other one, but this is a steady state calculator after all, doesn't really matter. But there's heat actually being put out. Okay. You see the white spots are slightly hotter. Okay, so this is another way to do radiation, another model. And we can just take a look at where these things are. We see that we have, in addition to G, we have this thing called iDefault, right? So iDefault is an input file you'll probably need for this finite volume method, discrete ordinates method. Okay, so we can take a look at the constant and see how the, oh, it's finished. We can see how the radiation properties are written. So we need coefficients. We have a radiation on and this radiation model. So we have to write everything in with the coefficients. Pretty similar input methodology. And we look at the boundary radiation properties, also about the same as the previous hot room case. And we take a look at the system and we see the FV solution. That's where the main changes are. So we take a look at this thing called II. So there is another entry we need to put in order for it to solve using this FVDOM method. And what else? We still need the G's, as we were talking about before. And this one, I lambda, needs to be put into this simple algorithm. And there's another I lambda entry down here. And that's all you kind of need to solve the thing using FVDOM. Finite volume discrete ordinates method. Okay, so that's just a basic run through. I'm not going to go through it in detail because the concepts are more or less there. You know, there are certain files you need to edit to put in a radiation model. That's not an issue. You can use snappy hex mesh with buoyantSimpleFoam as same as IcoFoam or PiezoFoam or PimpleFoam. No issue there. Next thing we want to look at probably is buoyant PimpleFoam. So I'm gonna stop here. This is probably the last time I want to be talking about buoyantSimpleFoam because we talked enough about steady state already. We want to look into non-steady state problems and see whether we can tweak a few tutorial files from there, or even make our own tutorial files where we can have a varying temperature boundary condition, because this again is a very interesting thing to explore, especially for research. Alright, so thank you very much. I'll see you guys next time.